Okay, hello and welcome to another video. This time I'm going to be taking you through the MAT 2012 question 3 question. I didn't mind this one. I thought part 3 was probably the hardest. Maybe part 5 can catch you out. It's not a bad question, but as always, it's a case of how well you can do in the stress of time conditions, which is not easy. Okay, let's get on with it. We've got a cubic. And they tell us it looks like this. Now, specifically, they're saying it has two distinct turning points, yeah? And that's because cubics can look like that, yeah? They don't have to have a minimum and a maximum. They can look something like that. Now, obviously, it's only when you've got a minimum and a maximum that you can have three roots for a cubic. And so it's certainly possible for a cubic to have just one root if it doesn't have a maximum or a minimum and it's shaped like that. I mean, just think of y equals x cubed as well, if you don't believe me here. The standard shape of y equals x cubed is it totally goes flat. The gradient is 0 at 0, but then it goes up like that. It does not have two turning points. Remember that for a polynomial of order n, it has at most n minus 1 turning points, and that's the key thing to remember here. Okay, now they've said that our form is like this, so we're dealing with f of x equals x cubed, and then it's plus ax squared plus bx plus c. And they want us to find the conditions on coefficients of a, b, and c, and there's somewhat of a, it doesn't end up being anything to do with c, this, so, somewhat off-putting that. But they need you to find a condition on the coefficients such that the curve has two distinct turning points. Well, if it has two distinct turning points, I'm firstly thinking, how do we find turning points? And we find them by differentiating. So I'm going to differentiate 3x squared 2ax plus b. And this is what I mean by it's definitely not dependent upon c, because c just moves the curve up and down. It doesn't actually change how many turning points there are. It simply moves the curve up and down. So it's actually nothing to do with c. Now, this equation should have two real roots, two distinct real roots, if it's going to have two turning points. So I'm just going to write that down. You wouldn't have to in the exam, but this should have two real and distinct roots. So this is a classic case of using the discriminant, yeah? And the first part of the question often is quite nice. Not always, but often it is. And so if I want this to have two distinct real roots, then b squared minus 4ac, which I'm going to put in inverted commas, has got to be greater than 0. Now, the reason I'm putting that in inverted commas is just because our a's, b's, and c's are not the same as our a's, b's, and c's up here. Your b, if you like, in this is 2a, which needs to all be squared, and then minus 4 times 3 times b, well, that's minus 12b. That needs to be bigger than 0. Hence, you end up with 4a squared is greater than 12b, or simply a squared is greater than 3b. You can see something like that is also the case later on in the question. Now, I've proved it here that if this is the case, that you've got a cubic like that, then the derivatives of that form, and therefore there should be two real distinct roots for the quadratic of that, for the discriminant, sorry, of that derivative, which happens to be quadratic, and then we derive this. Now, they did actually ask for an if and only if relationship to be demonstrated here. Now, I noticed in the mark scheme they didn't seem fussed about that at all, but I am quite fussy, and certainly if you do the step, they're mega fussy about always showing that the argument works in both directions. Now, all I'm going to do is just point out, well, on the other hand, remember that we were given this as well. We're allowed to use anything that we're given in a question because that's, it's just given, and f of x is given to be that. Well, I can say, on the other hand, if a squared is greater than 3b, and this, my argument here is just that it works perfectly the same backwards, then, and I'm just going to skip a few steps here, 4a squared minus 12b is bigger than 0. So the quadratic f dash of x, so if, let me put it like this, so if f dash of x equals 3x squared plus 2ax plus b, then it must have two real roots. And indeed, f dash of x does equal that. And I know I'm doing this really quite quickly because it's only worth a couple of marks in the exam, as, oh, sorry about that, terrible handwriting. Let me just fix that. Yeah, as the derivative does equal that, because look at the original function. Yeah. Now, I suspect, because of the way it's presented so quickly in the mark scheme, that they would let you get away with this if you just used if and only if statements all the way through this. If and only if that's true. If and only if that's true. Yeah, maybe they just want us to throw in a few of those if and only if statements. But I know certainly in STEP they like you to write the argument out in one direction and in the other. They're quite fussy about it in STEP, as they should be as well. I'm not criticising them there, but I'm just saying you might not be used to proving an argument in both directions. Okay, so that was that. So I didn't mind that at all. Now, let x1 and x2 denote the x-coordinate of a and b respectively. Show that this is true. Okay, this isn't too bad because naturally, in part 2, we're still dealing with the same quadratic. But we want to find the roots of the quadratic when it's equal to 0 now. And so our x values, if you like, x1 and 2, are going to be given by, and I'm just going to use the quad formula here, because, you know, the 3 there, otherwise I might complete the square, but I'm just going to use the quad formula, is minus b plus or minus the root of b squared minus 4a, which we've got up here. That's actually 4a squared minus 12b. Don't use the simplified version because we need to take the factor of 4 out of that, over 2 times the first coefficient, so that's 6. And so that's what x1 and 2 are. And specifically, you could say, okay, well, if you're looking at it like this, I don't know if they've labelled x2 and x1 here. Well, we clearly want it to come out positive. So if we have x2 as our first positive answer, minus 2a plus, and I'm going to take the 4 out and square root it to 2, a squared minus 3b. Now it looks a bit more similar to their answer, doesn't it? Over 6. Obviously, I can simplify that to minus a plus root a squared minus 3b over 3. Yeah. Now, what about x1? Well, x1 must be the other one, the one with a minus rather than a plus. And I'm just going to write it down straight away as minus a minus the square root of a squared minus 3b over 3. And alas, well, hence x2 minus x1 equals, okay, so I need to do minus a over 3 minus a over 3. Well, that becomes minus a over 3 plus a over 3, so the a's cancel. But then you've got a positive a squared minus 3b minus a squared, you know, root of a squared minus 3b, and that's going to become plus, so you're going to end up with 2 root a squared minus 3b over 3 as required. Okay, I'm just going to pause the video for a second because somebody's about to ask me a question. Okay, apologies for that. Somebody was just knocking on my door. Okay, so that gives us x2 minus x1, just as they told us it would be. Now, part 3. Suppose now that the graph is translated so that the turning point at A now lies at the origin. Let g of x be the cubic function such that y equals g of x has the translated graph. Show that this is the equation of g of x. Now, this is where I started to bump up against a bit of a problem. Mainly because my thinking initially, at least anyway, was, okay, I can translate this if I know A's coordinates, and I know A's x coordinates. Like, you know, if you let A's good, looking at that graph, it would be like minus a minus, it would be the smaller A value, you know, the smaller X value. And the trouble is, when you plug something like that into a cubic equation to find the Y coordinate, which is definitely going to be necessary if we want to work out the translation, you end up cubing a square root. It just didn't look like nice algebra. It really didn't, if you were thinking about doing it that way. So that thought did cross my mind, but it just looked like too much of a nasty kind of approach. But the second thing which is in the back of my mind is we want to make sure that our function has a on the origin now. Well, that means it has a repeated root at the origin, which is exactly what g of x is showing, and that's why I eventually went with this approach. I thought, well, we can see, as it's a translation of f of x, and has a repeated root at the origin, it must be of the form and then I called it y equals, or g of x equals as they use in g of x equals x squared x minus p. Yeah. Now, I was worried about maybe writing a capital letter down here first, like ax squared x minus p, but that's not necessary because we know it hasn't been stretched. Yeah, it was a 1x cubed up here, so it should be definitely of that form. And now we've just got to find p, hopefully, as root a squared minus 3b. Now, I was quite stuck here as well. This wasn't the easy bit of the question. This was the toughest bit. I think this was the worst bit for me. But eventually I realised, well, hang on a second. This part 2 hasn't been done for no reason at all. It's weird how they made us subtract these. And the reason why they've made us subtract these is because this distance from here to here is, of course, x2 minus x1. Yeah? Oh, that's not very clear. Let me just try and write that again. So let's say, and you can see this, yeah? Let's say your graph looks something like that. You know, the distance from here to here is, if B is on x2 and A has a coordinate of x1, it would be x2 minus x1. Yeah? So that's the width between the two turning points. And naturally, once you've translated it so it's on the origin A, you now know that B's coordinate will have an x coordinate of x2 minus x1. Yeah? And a y coordinate of, I don't know, let's call it y hat. Yeah, but we know that's going to be the correct x coordinate for B. So what I can now do, once I realise this, I really got going on this question, is point out, well, we know that P equals P's x coordinate, if you like. Oh yeah, sorry, yeah. Let's not get confused here. Where is P on that graph? Sorry, the turning point here, that's the point. P, of course, is here, yeah? So this has nothing to do with P, but we can work out P now because we now know that the turning point is there. And that's very good because what we can do is we can differentiate this. G dash of x is going to be, should we use product rule? 2x, x minus P plus 1 times x squared, so plus x squared. Don't know why I did that. You're going to end up with 3x squared minus 2px. And this should equal 0 when x equals 0, well, clearly that's the solution, or when x equals x2 minus x1, in other words, 2/3 root a squared minus 3b. So do you see what I mean? Because we know the coordinate of the turning point now, we can plug that in here. And so what I can do is say, okay, oh, and I should have factorized this as well. It makes it slightly easier to see what's going on. I can see now that 3x minus 2p, well, here x is 2p over 3, isn't it? But we know that that 2p over 3 equals this. So 2p over 3 equals 2/3 root a squared minus 3b. And that leads straight to the answer as given. And so p is going to be equal to root a squared minus 3b. And therefore we have it. Hence g of x equals x squared x minus root a squared minus 3b. So just to summarise that argument, what have I done there? Well, I've realised it was a good reason they got us to do x2 minus x1. It's the width between the turning points. So if this one's on the origin, the other one will have an x coordinate of x2 minus x1, which is here. And then I've differentiated g of x, made it equal to 0. In other words, I'm finding the turning points. I've found one of the turning points in terms of p, but I already know where it is, so I can then find the value of p, and it's done. Okay, part 4. What have we got here? Here we are. R is the area enclosed by the region, by the x-axis, and the graph y equals g of x. So R is this region here. Yeah? And they want us to show that if A and B are rational, then R is also rational. Well, remember R is an area, so it's going to be the negative of integrating from 0 up to, now let's get right here. We now know what P is. It's root a squared minus 3b. So I can write that down as root a squared minus 3b. I've put a minus sign outside because this should turn out to be negative because the area is underneath the x-axis. So if I put a minus there, this is now a positive area. And I need to integrate x squared x minus p. Cool. So that's what I'm going to do. So I integrate it. And as you can see, that's going to become x cubed minus x squared p. So I think I can integrate that in my head to x to the 4 over 4. That's the result of integrating x cubed. And then I've got minus x squared p. Well, that's minus x cubed over 3p between root of a squared minus 3b and 0. Yeah? Well, that is the minus of, now let's do this carefully. Now, if you stick that in there, you get a really quite a nice way of writing it. A squared minus 3b all squared, because we're doing the power of 4 and a square root, and that's the power of a half. So this is going to be squared. Minus, now, what are we going to have here? Well, we're going to have root of that cube. So it's going to be a squared minus 3b to the 3 over 2. But then we're timesing it by p, which is this. This is p. And so it's going to be times by root a squared minus 3b. And so that's going to end up being also to the power of 2. And when you plug in 0, you get 0 for both. And so we end up with, we can basically do it now, because you could take out the a squared minus 3b squared, because that equals, after you've times it by that, a squared minus 3b all squared. And then you've just got to do a quarter minus a third. Well, a quarter minus a third is going to be 3/12 minus 4/12, and so it's going to be minus 1/12. So this becomes that over 12. Yeah, after you've applied the negative. Okay, now why is it if a and b are rational, this is rational? Well, clearly, well, all the square roots have gone. That's the reason why, really. Okay, so if a squared and b are rational, I think they just said a and b, didn't they? Not a squared and b. Let me get it right. Yeah, show that if a and b are rational, r is also rational. I'm just going to say at the end, so if a and b are rational, then a squared minus 3b squared is certainly rational. Hence r is rational. It's obvious now. Cool. And then they ask this cryptic little question. Is it possible for r to be a non-zero rational number when a and b are both irrational? Justify your answer. Well, this doesn't feel like the rest of the question. You've basically got to try and find sneaky values which make this rational when a and b are irrational, because they're saying, is it possible? And it's like, actually, I think I can make it possible, because if I had a as something like the 4th root of 2, yeah, and b as the square root of 2, I think I'm going to be all right here. And I'll tell you why I did that, because if you multiply this out, you get a to the 4 minus 3a squared b, minus 3a squared b, so that's minus 6a squared b, plus 9b squared. Now, if a and b were irrational, like root 2 or something like that, the obvious thing would be to give them root 2, and then that's going to be rational. But it's the middle term there. If you used root 2, sure, the a squared is going to get rid of the root, but there's still going to be a surd basically on the b, and that's what's going to cause it to be irrational. So we need to make sure and try and avoid b being irrational here. Well, if you think about it, if you let a be the 4th root of 2, then after you square it, you've got the square root of 2 here times the square root of 2, and then r is rational still. This gives a rational value of r as, you know, a to the 4 is rational, b squared is clearly rational, and this was the stumbling block, 6a squared b is rational too. And so, yes, it is possible. So it is possible. And that's this question. I didn't think it was too bad in the end. It's different, of course, when you're doing it in test conditions. It's really hard. But hopefully that all makes sense. Let me know in the comments if you're confused about anything. Well done.